Hi friends, in this session we consider continuity and differentiation of functions of complex variable. First we have continuity. Definition: a function fz is said to be continuous at a point z is equal to z0 if f of z0 exists. First one, f of z0 exists. Second one, limit z tending to z0 fz exists. Third one, limit z tending to z0 fz is equal to f of z0. That is, f is continuous at z0 if f of z0 is defined and also limit z tending to z0 fz is equal to f of z0. Formally, fz is said to be continuous at a point z is equal to z0 if for every positive real number epsilon, no matter how small epsilon is but not 0. We can find a positive real number delta such that mod fz minus f of z0 less than epsilon whenever mod z minus z0 less than delta. That is 0 less than mod z minus z0 less than delta. Mark it as equation number 1. We observe that in the definition of limit of f at x0, for each positive number epsilon, there is a positive number delta such that mod fz minus w0 is less than epsilon whenever 0 less than mod z minus z0 less than delta. That is, we take deleted delta neighborhood of z0, while in definition of continuity, we take the delta neighborhood of z0. A function of a complex variable is said to be continuous in a region R if it is continuous at every point in R. Next we have an example. The function fz is equal to xy square plus I into 2x minus y is continuous in the complex plane because for any point z0 is equal to x0 plus I y0. We have f of z0 is equal to x0 y0 square plus I into 2x0 minus y0. This one exists. And also limit z tending to z0 fz is equal to x0 y0 square plus I 2 x0 minus y0 which is equal to f of z0. That is, limit z tending to z0 f of z is equal to, we have f of z0. Next we have an example. Fz is equal to e raised to xy plus I sin x square minus 2xy cube is continuous in the complex plane because for any point z0 is equal to x0 plus I y0. We have limit z tending to z0 fz is equal to e raised to x0 y0 plus I into sin x0 square plus, sorry, here we have minus 2 x0 y0 cube, which is same as f z0. We recall result in the case of limit of functions of complex variable. Suppose that fz is equal to uxy plus ivxy and also z0 is equal to x0 plus iy0 and w0 is equal to u0 plus iv0. Then limit z tending to z0 fz is equal to w0. This is if and only if limit xy tending to x naught y naught u xy is equal to u naught and limit xy tending to x naught y naught v xy is equal to v naught. If f is continuous at z naught is equal to x naught y naught, then limit z tending to z naught f z is equal to w naught, which is equal to f of z naught. Limit xy tending to x naught y naught u xy is equal to u of x naught y naught, and also limit xy tending to x naught y naught v xy is equal to v x naught y naught. Hence, we obtain a theorem. That is a function f z, that is f z is equal to u xy plus I v xy is continuous at a point z naught is equal to x naught y naught if and only if its components functions u and v are continuous there. We have a remark. In view of theorem 1, the function f z is equal to xy square plus I into 2x minus y is continuous everywhere in the complex plane because the component function xy square and 2x minus y are polynomials in x and y and are therefore continuous at each point xy. Limit laws of sum, product and quotient leads to the following theorem. Next we have a theorem. That is, if two functions are continuous at a point, their sum and product are also continuous at that point. Their quotient is continuous at any such point where the denominator is not 0. Next we have continuity of the composition of two continuous functions. We have a theorem. The composition of two continuous functions is continuous. Proof follows that let f z be a function defined for all z in a neighborhood of a point and we let g z be a function whose domain of definition contains the image of that neighborhood. The composition g composition f of z is equal to g of f of z is then defined for all z in the neighborhood of z naught. Suppose now f is continuous at z naught and g is continuous at the point w naught is equal to f of z naught. In view of the continuity of g at w naught is equal to f of z naught, we know that for each positive number epsilon, there is a positive number r such that mod g composition f of z is equal to, g composition f of z minus g composition f of z naught, g composition f of z naught is equal to g of f of z minus g of f of z naught it is less than epsilon. Here of course we have modulus less than epsilon. Whenever we have mod f z minus f z naught less than r. Here we can find a figure, that is, this is our x y plane. Here we have z naught, this is our delta, here we have 1 z. This is the distance between z naught to the circle is delta, and again here we have f of z naught, here we have f of z, and distance between f of z naught to the circle, here we have distance R. And the composition we have here we have G of f of z naught, here we have G of f of z, and the distance between the center G f of z naught to the circle is epsilon. Okay. Combining all the above, we have corresponding to each positive number epsilon, there is a positive number delta such that G composition f z minus G composition f z naught is less than epsilon whenever mod z minus z naught less than delta, showing that G composition f is continuous at z naught. Hence, the composition of two continuous functions is again continuous. Next, we have another theorem. If a function f z is continuous and non-zero at a point z naught, then f z not equal to 0 throughout some neighborhood of that point. That is, f z not equal to 0 for every z in some neighborhood mod z minus z naught less than delta of z naught. We have the proof. First, assume that f z is continuous at point z naught. Then, corresponding to any given epsilon, there exists a delta greater than 0 such that mod f z minus f z naught, it is less than epsilon whenever mod z minus z naught less than delta. Since f z is non-zero at z naught, we have mod f of z naught greater than 0. We let epsilon is equal to this one, what, mod f of z naught by 2. Can take epsilon is equal to mod f of z naught by 2. Then, corresponding to this epsilon, there exists a delta greater than 0 such that mod f z minus f of z naught less than mod f of z naught by 2, that is our epsilon, whenever mod z minus z naught less than delta. Hence, it follows that f of z not equal to 0 at any point in the neighborhood mod z minus z naught less than delta. Because if f z is equal to 0, the inequality above gives mod f of z naught less than mod f of z naught by 2. That is mod f of z naught which is less than mod f of z naught by 2. It's a contradiction. So, we have the proof. Next, we have a definition. A region R is closed if it contains all of its boundary points. It is bounded if it lies inside some circle centered at the origin. So, a theorem. If a function f is continuous throughout a region R, that is both closed and bounded, there exists a non-negative real number capital M such that what, mod f of z is less than this M. For all points z belongs to R. For every z belongs to R. Where equality holds for at least one such set. Here we have R plane. Proof. We assume that the function f given by f z is equal to u x y plus I v x y is continuous, and hence the function square root of u x y whole square plus v x y square being the composition of two functions, two continuous functions is continuous throughout R and thus bounded and reaches a maximum value m somewhere in R. That is, this square root of uxy whole square plus vxy whole square is always less than or equal to m. Of course, here we have modulus. Modulus value is always less than or equal to m for all points z is equal to x plus iy belongs to R. Since mod fz is equal to mod square root of uxy whole square plus vxy whole square, the above can be written as mod fz less than or equal to m. That is mod fz we have less than or equal to m for all points z belongs to R. Where equality holds for at least one such set. Okay. Next we have derivatives. Derivatives. Let f be a function whose domain of definition contains a neighborhood of a point z0. The derivative of f at z0 written by f dash z0 is defined by the equation f dash of z0 is equal to, which is equal to limit z tending to z0 fz minus f z0 divided by z minus z0. Mark it as equation number 2. Provided this limit exists. By expressing the variable z in the definition of derivative in terms of the new complex variable delta z is equal to z minus z0. That is delta z which is equal to z minus z0. We can write the above definition as f dash of z0 is equal to limit delta z tending to 0 f of z0 plus delta z minus, instead of f of z0 we have f of z0 divided by we have delta z. That is delta z is actually z minus z0. Here note that since f is defined throughout a neighborhood of z0, the number f of z0 plus delta z is always defined for mod delta z sufficiently small. We introduce the number delta w. Now we introduce delta w is equal to f of z plus delta z minus f of z, which denote the change in the value of f corresponding to a change delta z in the variable z. Then if we write dw by dz for f dash of z, then we can write f dash of z is equal to dw by dz, which is equal to limit delta z tending to 0, limit delta z tending to 0, delta w by delta z, or this we can write as limit delta z tending to 0, we can write delta w by delta z as f of z plus delta z minus f of z by delta z. Next we have an example. Find the derivative of fz is equal to z square at any point z. At any point z we have fz is equal to z square. So, f dash z is equal to of course dw by dz, which is again limit delta z tending to 0 delta w by delta z, which we can write f dash z is equal to, we can write limit delta z tending to 0 delta w by delta z, which we can write f of z plus delta z minus f of z by delta z, that is limit delta z tending to 0 f of z plus delta z minus f of z by delta z, which is equal to limit delta z tending to 0, which is again limit delta z tending to 0 z plus delta z whole square minus z square by delta z. That is, here we have f z is equal to z square. So, we can write z plus delta z whole square minus z square by delta z. On expanding, we have limit delta z tending to 0. This is z square plus a plus b whole square form, z square plus 2z delta z plus delta z whole square minus z square by delta z. On simplification, we get limit delta z tending to 0, delta z tending to 0, 2z delta z plus delta z whole square by delta z, which is equal to 2z plus, simplification we get 2z plus delta z is equal to 2z. Limit delta z tending to 0, we have the answer is equal to 2z. Next we have an example. If f z is equal to mod z square, we show that derivative exists only at the origin. That is, f z is equal to mod z square. Taking w is equal to f z and delta w is equal to of course f of z plus delta z minus f z, we have delta w by delta z is equal to delta w by delta z is equal to mod z plus delta z whole square minus mod z square divided by delta z, which we can write as z plus delta z into z plus delta z conjugate. Here we have z plus delta z whole square, we can write as z plus delta z into z plus delta z conjugate minus of course mod z square, we can write z conjugate divided by delta z, which we can write as, again by simplification we can write this as z into z bar plus z bar into delta z plus z into delta z bar plus delta z into delta z bar minus z bar by delta z, which is equal to, on simplification we get, which is equal to z bar into delta z plus z into delta z bar. Here we have z bar into delta z plus z into delta z bar plus delta z into delta z bar minus z bar, okay, minus z bar and plus z bar get cancelled. So, here we have z bar into delta z plus z delta z bar plus delta z into delta z bar divided by delta z, which is again is equal to z bar plus delta z bar z bar plus delta z bar plus z into delta z bar by delta z. This is equation number 1, new number 1. We first consider the case when the point is the origin. At the origin, we have z is equal to 0 and z bar is equal to 0. Therefore, the equation reduces to delta w by delta z. That is, where z is equal to 0 and z bar is equal to 0, this reduces to it is equal to delta z bar. Hence, dw by dz is equal to limit delta z tending to 0, delta w by delta z, which is equal to limit delta z tending to 0, delta z bar, which is equal to 0 at the origin. That is, the value dw by, this is dw by dz. dw by dz is equal to 0 at the origin. Now, we consider the case when the point is not the origin. We claim that limit of 1 does not exist when z is a point other than the origin. We prove our claim using two-path test for non-existence of limit. If the limit of delta w by delta z exists when z not equal to 0, that limit may be found by letting the variable delta z is equal to delta x plus I delta y approach 0 in any manner. In particular, when delta z approaches the origin horizontally through the points delta x0 on the real axis, we may write delta z conjugate is equal to this is equal to delta x plus I delta y conjugate, which is again is equal to delta x plus 0 y, which is equal to delta z. Here, using 1, if the limit of delta w by delta z exists, its value must be limit delta z tending to 0 z bar plus delta z bar plus z into delta z bar by delta z, which is equal to limit delta z tending to 0 z bar plus delta z bar plus z into delta z by delta z. So, here we have only delta z, that is, which is equal to limit delta z tending to 0, which is again equal to limit delta z tending to 0. We have here we have z bar plus delta z plus z. That is, which is equal to z bar plus z. As delta z approaches to 0, here we have which is equal to z bar plus z. This is equation number 2. However, when delta z approaches the origin vertically through the point 0 delta y on the imaginary axis, so that we have delta z bar. Delta z bar is equal to 0 plus I delta y bar, which we can write as which is equal to minus delta z. And using the equation number 1, if the limit exists, its value must be limit delta z tending to 0 z bar plus delta z bar plus z into delta z bar by delta z, which is again which is equal to this is equal to limit delta z approaches to 0 z bar minus delta z plus z into minus delta z by delta z. This is minus delta z, which is on simplification we get, which is limit delta z tending to 0 z bar minus delta z minus z. That is, which is again equal to z bar minus z. We have next equation number 3. Since a limit is unique, it follows from 2 and 3 that we have z bar plus z is equal to z bar minus z, which gives what? Which gives we have 2z is equal to 0, which implies z is equal to 0 if dw by dz exists. But this is a contradiction to the fact that z not equal to 0. This contradiction leads us to state that dw by dz exists only at the origin. So, we have some remarks. The above example shows that a function can be differentiable at a certain point, but nowhere else in any neighborhood of that point. Next one, also for the function f z is equal to mod z square, since real part of f z is equal to x square plus y square, and also imaginary part of f z is equal to 0, respectively, it shows that the real and imaginary components of a function of a complex variable can have continuous partial derivatives of all orders at a point, and yet the function may not even be differentiable there. Next example. If w is equal to f z, which is equal to f z bar, show that we have to show that dw by dz does not exist at any point. dw by dz does not exist. We have to show this. Here we have f z is equal to z bar, which we can write as f z, we can write as x minus iy, that is z bar. We write delta z is equal to delta x plus I delta y. And obtain f of z plus delta z minus f z by delta z as which is equal to z plus delta z bar minus z bar by delta z, which is delta z bar by delta z. Which is again we can write this is equal to delta x minus I delta y by delta x plus I delta y. Mark it as equation number 1. If delta y is equal to 0, this is plus 1. If delta x is equal to 0, this is minus 1. Thus, one approaches plus 1 along the path 1 along the first path. That is, here we have a figure. Here we have z and z plus delta z. This is our path 1. This is our path 2. That is, this one approaches plus 1 along path 1, that is here through path 1, but minus 1 along path 2. Hence, by definition, the limit of first equation as delta set tending to 0 does not exist at any set. Next, we have a theorem. Theorem. The existence of the derivative of a function at a point implies the continuity of the function at that point. That is, suppose f is differentiable at a point z0, then limit z tending to z0 f of z minus f z0 by z minus z0 exists and is equal to f dash of z0. We write limit z tending to z0 f of z minus f of z0 is equal to this way I can write, which is equal to limit z tending to z0 f of z minus f of z0 by z minus z0 by z minus z0 into z minus z0, multiplying, dividing by z minus z0. That is, which is equal to, which we can write, which is equal to limit z tending to z0, we can split f of z minus f of z0 by z minus z0 again we have limit z tending to 0 z minus z0. This is equal to what? Here we have, this is equal to f dash of z0 into 0. This is 0. So, this is equal to 0. Hence, we have limit z tending to z0 fz is equal to f of z0. This implies that fz is continuous at z is equal to z0. This completes the proof. And also, converse of the above is not true. The continuity of a function at a point does not imply the existence of a derivative there. For example, the function fz is equal to mod z square is continuous at each point in the plane, but not differentiable except at the origin. Next, we have differentiation formula. Differentiation formula. Theorem. Let C be a complex constant and let f be a function whose derivative exists at a point z. Then we have the following formulas. D by dx of c, d by dz of c is equal to 0. First one, d by dz of c is equal to 0, where c is a constant. Next one, d by dz of z is equal to 1. Next we have d by dz of c fz is equal to c fz, which is equal to c into d by dz of f of z. And fourth one, if n is a positive integer, d by dz of z raised to n is of course n into z raised to n minus 1. Here n is a positive integer. The last formula remains valid when n is negative integer provided z not equal to 0. Chain rule we will discuss. Suppose that f has a derivative at z naught and that g has a derivative at the point f of z naught, then the function f z, we can write f z is equal to composite function g composition f of z, or we can write it as g of f of z, has a derivative at z naught and d by dz of f z naught is equal to derivative of f z naught, which is equal to d by dz of course d by dz of g composition f of z, which is again d by dz of g of f of z. That is, here we can use the product rule, that is d by dz of g of f of z naught into d by dz of f of z naught. G of f of z into g of f of z naught, here we have z naught into d by dz of f of z naught. Okay. If we write f dash z for d by dz of f z, we get, that is f dash z instead of d by dz of f z. That is, we get f dash z naught is equal to g dash f of z naught into f dash of z naught. That is, by using d by dz f z is equal to f dash z. We have, this is g dash of f of z naught into f dash of z naught. This is equation number 1. Also, if we let w is equal to f of z and capital W is equal to g of w, then at the point z, the chain rule 1 becomes this chain rule 1 becomes dw by dz, which is equal to dw by dw, here we have capital W, dw by dw into dw by dz. Next we have an example. As an illustration of chain rule, we have to find the derivative of 3z square plus 5y whole cube. That is, we want the derivative of 3z square plus 5y whole cube. We write w, we can write w is equal to what? 3z square plus 5y. Only this one, 3z square plus 5i, 3z square plus 5i, and capital W is equal to this w cube. W cube. Then we have dw by dz is equal to we can write this is equal to chain rule dw by dw into dw by dz, which is again d by dw of w cube d by dw of w cube into dw by dz. This we can write as 3w square, that is d by w of w cube, we have 3w square into dw by dz. which I can write as dw by dz as, here we have w is equal to 3z square plus 5y. So, 3w square into dw by dz I can write as 3 into 3z square plus 5y square, 3 into 3z square plus 5y square into d by dz of, instead of w I can write it as 3z square plus 5y. Which on simplification we get, which is equal to 3 into 3z square plus 5y whole square into 6z. That is d by dz of 3z square, we have 6z. So, altogether we have the result, it is 18z into 18z, 3 into 6, we have 18z into 3z square plus 5y whole square. So, in this session we have discussed continuity and derivatives, and also last we have chain rule also. Next we will discuss about Cauchy-Riemann equations. So, till then take care, bye.